So this is going to take about 45 minutes, and then we'll leave good 10 minutes at the end for questions if we have time. So without any further ado, I want to introduce Phil Gutowski. He is our founder of BoatRx. He's also a 3-time IBEX Innovation Award judge. And this talk was actually supposed to be given at IBEX this year, but as we know, the hurricane kind of ended those plans pretty quickly. Phil is also a technical writer for Sail Magazine, and he was actually an award judge for the best boat this year. So without any further ado, I'll hand things over to Phil and spotlight him. Phil, you're muted, so there you go.
Hey, everybody, you hear me?
Hear you great.
Welcome, everybody. Thanks for taking a few minutes out of your day. And in the next 45 minutes, I'll talk about why we need to rethink the existing ways how we design power systems for boats, and why new air conditioning technology is flipping the script on the way we think about this electrical power. Then we'll review one of the recent projects we did at BoatRx, and I'll walk you through the steps from start to finish and share all of our secrets of how we design and install 24-hour climate control in a boat that doesn't require reliance on a separate generator. As you can see all around you, it's undoubtable that there's a shift to electrification. You or your neighbors might already have solar panels on your house. You might have a backup battery in your basement. You or somebody you know might already drive an electric car. Electrification is arriving to every motive industry market, and it's beginning to hit boating in a big way. In fact, you might notice when it comes to the electrification of boating, there's been a ton of attention, especially in the media outlets, of new investment being paid to electric propulsion systems. But I feel that before we go all electric in that sense, there's still a ton of room for efficiency gains in the onboard comfort systems. If you consider that most new luxury boats, both power and sail, are air conditioned, and that air conditioning is in use almost all of the time, it accounts for the most power that's consumed on board these boats. So where does that power come from? Of course, if we're not plugged into shore power, we're running generators. And the thing is that these generators, they have to be so oversized in the boat to meet the electrical needs of all the appliances when they're all turned on. That includes the air conditioning and traditional stop-start air conditioners, the kind that turn on and off when they reach set temperature, the kind that are still installed in many modern boats today. They actually draw even more power when they go to start up. We call this inrush current. And so when we size a generator for the boat, we figure out, okay, what do all the appliances use when they're all turned up to 11? And then we size it even further for the inrush current to make sure that the generator can run all the loads in the boat. The thing is that the generator it's just not operating under this full load condition all the time, right? In fact, most of the time, we're only using a small portion of the power that generator is producing. So if you take a look at this chart, you can see that on the left and on the y-axis, you have the fuel consumed in grams per kilowatt hour, and the x-axis, the applied load. You'll find that the graph starts up very high, meaning that the lower the load that's on the generator, the more fuel we're consuming for the amount of power that's produced. And these diesel generators only reach their peak efficiency when they're loaded with a force that's almost equal to their rated capacity. So on average, boat owners are paying between $3 and $9 per kilowatt hour generated under these low load conditions. This is a crazy number, and the calculations came from our friend and everybody's favorite systems guru, Nigel Calder. It's so crazy because at home, most of us are paying like 10 to 13 cents per kilowatt hour. And I kind of didn't believe this, so I pushed Nigel on these figures, and he reminded me that it's the amortization cost of the generator combined with those low average loads, which drives this kilowatt hour cost through the roof. So this existing generator-based power system design is so backwards. There are just several things in the industry that we're doing that just really don't make sense. For example, I know captains and boat owners who, when they go and turn on their generator, they then go and turn on everything in the boat. They turn on all the air conditioners. They might start cooking in the galley. Maybe it's time to blow dry your hair. This is teaching us to use more power than we need. I mean, can you imagine if you did that at home? If you flipped on the light switch to your living room, then you proceeded to go around the house and turn on everything. You started the microwave, turned on the oven, and you went to blow dry your hair and made some toast. I mean, that's not how electrical power is supposed to work. And on bigger yachts, we have these load banks that heat up seawater and discharge it overboard just to keep the generator happy. I mean, I think if your friends who are outside of our industry saw this, they would be like, what are you guys doing? So is anybody catching the hint that I'm not a big fan of generators? I mean, this is the age of electrification, right? And I know what you might be thinking, that, well, there's lithium batteries now, right? We can put a big battery bank in and we can use inverters and run everything off the inverters, and that solves the problem. Well, I mean, everybody knows lithium batteries the technology is dramatically improved and it's enabling all these new technologies. But that's not what I'm here to talk about. This is not about the battery. You see, the secret to battery-powered air conditioning is air conditioning. If we want to run an air conditioning system without starting a generator, we need that air conditioning system to use as little power as possible. So I want to introduce you to the most efficient type of air conditioning that's available today. It's called variable refrigerant volume, VRV, also known as variable refrigerant flow, VRF. Those are interchangeable terms. On the screen, you can see these Mitsubishi land-based systems that are pictured. And you might recognize some of these components. You've often seen these installed in residences or commercial buildings. You might be familiar with the terms inverter mini splits or ductless air conditioning. When we're talking about those things, we're talking about the same technology. And but VRV it's just a little more scalable than a simple mini split. It can be installed in small residences or large commercial applications like hotels, schools, high-rise buildings. And the technology is not new. VRV systems have really caught on outside the US. And they make up 85 to 90% of the new air conditioning systems that are in Europe and Asia. And even back home here in the United States, VRV systems have been in the ASHRAE handbook since 2012. And ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And just like the ABYC produces a standards that we follow in the marine trades, ASHRAE produces is the trade handbook for the HVAC trade. So they've been talking about VRV and it's in the standards since 2012. I also want to use this opportunity to distinguish the VRV system that I'm about to talk about from existing marine self-contained units, which oftentimes also use variable speed technology. That word variable has kind of become a buzzword in our industry. And it's for good reason. I mean, the modern self-contained units that you see pictured on the screen here are leaps and bounds better than the traditional start-stop air conditioners we've used for so many years. These are called self-contained because the compressor, condenser, the evaporator, and the blower, they all live in the same package. And so when we're installing self-contained units, those need to be, there needs to be one of these units for every zone. Additionally, self-contained units can operate on different sources of power. And what's becoming super popular are DC powered air conditioners, DC powered self-contained air conditioners, especially the 12-volt units. The unit in the middle there with the copper coil, that's a 12-volt air conditioner from Meru Power Systems. And at BoatRx, we install a ton of those, and we really love the product. They're especially well suited for smaller boats or smaller air conditioning demands, especially, for example, like a small power boat with a cuddy cabin, where we can put in a single 12-volt air conditioner. We can do a little bit of an upgrade to the battery bank, and without having to really re-engineer the boat's electrical system, that upgrade can be done relatively simply. When we get to higher air conditioning demands, we're using higher voltage equipment, and the VRV systems run on 230 volts. And we run that, of course, through an inverter. And modern inverters are about 95% efficient. So the 5% loss that we're getting in converting the power from DC to AC is vastly outweighed by the efficiency gains from switching to a VRV system. So here's a little diagram of a VRV system, which is different from self-contained. VRV uses advanced software that precisely controls the flow of refrigerant from a central compressor to many individual air handlers. And every part of the system is connected to a common controls network. So it's software that's processing the data from a number of temperature and pressure transducers throughout the system. and makes changes to compressor speed, fan speeds, and expansion valve positions in real time to maximize the comfort and efficiency of the entire system. So we're moving refrigerant around through the system from a central compressor in order to move heat around through the system. We're always using in the air conditioning mode, we're extracting heat out of the air and we're trying to transfer it back to the seawater. You're going to hear us talk about refrigerant a lot. And what is refrigerant? Well, some people know it as Freon. Freon or refrigerant, it's just this chemical compound that was specially designed to exist easily in two different states of matter, gas and liquid. And we can convert it between those two states of matter by altering its temperature and its pressure. And every time it moves from a gas to a liquid or a gas, it's either absorbing or releasing heat energy. And that's a huge part of how air conditioning systems work. So I'm going to stay on this slide for a second. I hope I don't lose you because I'm about to get technical, but it's important that we walk through quickly the path of refrigerant flow through the system. So if we start at the compressor, the refrigerant exits the compressor as a high pressure, high temperature gas. That high temperature, high pressure gas enters the refrigerant condenser, which is a heat exchanger, where it interfaces with seawater, which cools the refrigerant down below its saturation point, its dew point, and converts it to a liquid. Now that liquid refrigerant simply travels out that orange liquid line through a network of pipes, which we use a flexible refrigerant hose, by the way, and is delivered to each air handler, which is installed in the various zones in the boat. When that liquid refrigerant encounters the air handler, it first meets what's called an EEV, or an electronic expansion valve. And that EEV, much like your thumb over the end of a garden hose, is restricting the flow of that liquid refrigerant and literally spraying it into the coil where it drops its pressure on the other side. And when it does so, the pressure drop induces it to change states of matter again from liquid back to vapor. And in doing so, it absorbs heat from the coil and gets really cold. Well, we blow air across this cold coil, and that's how air conditioning works. The final step is that vaporized refrigerant travels back down that blue suction line, returns to the compressor, and starts the process all over again. The thing that's special here is that this is an integrated system, and the software controls are always regulating the compressor speed and the valve positions and the fan speeds to match the ever-changing heat load and always maximize efficiency. So here's one of my favorite things about the VRV system, is that since this capacity is on demand, the refrigerant will always be directed to where it's needed most. And if the air handler coil is running warmer, that valve opens up and feeds a little more refrigerant into it. And if it's running colder, it restricts and it closes down. So if you look at this power yacht that's on the screen, we have really individualized control of the different comfort zones. And if you were to imagine cooling this with self-contained units, you'd need about 7 self-contained units, each with 7 compressors and 7 sets of seawater hose delivered to each zone. And the VRV system just uses the one compressor, the various air handlers, and we can even oversize the air handlers for various zones and exceed the air handler capacity over the compressor capacity. So if we need more cooling in one zone, like say on the bridge deck in the sun during the day, we can drive a majority of the cooling up to that space, scavenge it from the areas that don't need it, and keep the vessel cool without really increasing our power consumption. I'll also mention that boats like this often also use chiller systems which circulate 55 degrees seawater or fresh water in a chiller loop. That's the topic for another day, and it's beyond the scope of this talk, but I did want to mention that. Let's also talk about humidity, which is also critical for comfort. In order to dehumidify the boat, we need to condense water vapor out of the air. To condense water vapor out of the air, we need to cool it down below its dew point, where that water will collect as liquid on the cold surface, just like the water that's dripping on the outside of your cold beer can. The VRV system excels at this. Because the temperature of the coil is so precisely regulated, we can bring the coil temperature down to about 33 degrees, just above freezing, and maximize the dehumidification effect. And here's the thing about dehumidification as it pertains to all air conditioning systems. it uses a lot more power to remove water vapor out of the air than it does to lower the air temperature. Okay, so if we get our cabins dehumidified, it takes a small amount of electrical power to maintain that temperature once we removed what we call the latent heat out of the boat. Okay, and if the boat is, say, a sailboat, and they have the air conditioning system off while they're out sailing, but then they drop the sails, start the engine and motor into the anchorage. If the operator also cranks up the air conditioning while we have surplus power available from the alternators, now we're dehumidifying the boat off of surplus energy so that after the hook is dropped and the engine gets shut off, now we can run on battery power with very little consumption to maintain at that temperature because the boat's already been dehumidified. Now, when it comes to power consumption, I can tell you from standing around at the boat shows that everybody wants to ask, how much power does he use? How much power does he use? And the truth is, it's not just really effective to look at the maximum power draw of any system. I mean, taking a snapshot of the power consumption is not the same as monitoring its usage over the time. And the VRV is exceptional at maximizing the efficiency over a long period of time. But I do want to show you some quick examples of the new VRV8 compressor paired with 3 air handlers from Thermodynamica at its maximum power draw, 1500 watts, versus some competition, both variable speed competition and traditional self-contained. And when compared to traditional self-contained units, the Thermodynamica system is often close to 70% more efficient, more power efficient than the old style units. And compared to modern variable speed self-contained units, we're at least 20% better. So how do we do it? Well, a company like Thermodynamica, who's making these VRV systems, they are an innovation-based company, and there's a ton of engineering that's going into every part that goes into the system. And it's all these small improvements of every component that together make up the radical innovation that is VRV air conditioning. So for example, even the simple mechanical component like the condenser, which doesn't have any software or any smarts, it's just the dumb piece of metal, it gets special attention and special engineering. All right, let's get technical one more time. If we know that the refrigerant that's coming out of the compressor is at a high pressure, that means that the compressor motor has to push against that high pressure refrigerant. Okay, so there's a lot of electrical torque on that motor, and the higher the electrical torque is on the compressor motor, the higher the power consumption is. But why do we need the refrigerant to be such a high pressure? Well, it's because with high pressure comes high temperature, and we need to maintain the refrigerant temperature well above the seawater temperature so that when it interfaces in the condenser with the seawater, heat is transferred from the hot refrigerant to the cool seawater. So if we simply lower the pressure coming out of the compressor, we could save power, but we're not transferring heat anymore. We're no longer getting the refrigerant to condense from gas to liquid in the condenser. But what Thermodynamica has done is they figured out how to make an extremely efficient condenser, about 40% better than the competition. And by doing so, the temperature differential between the hot refrigerant and the cool seawater can now be smaller because the condenser does a better job at transferring that heat. If the temperature differential can be smaller, we can function with a lower temperature refrigerant, which equals a lower pressure refrigerant coming out of the compressor, and lower pressure equals lower electrical torque on the motor, and lower electrical torque on the motor equals lower electrical power and a total reduced power. All right. There are some limitations with any new technology. The thing I want to point out about these VRV systems is at the moment, they've got to be professionally installed, and the commissioning has to be performed by an experienced HVAC technician. At the moment, we're interested in working with more boatyards and training them to do the first 90% of the installation. And our team will come and actually do the commissioning and work with the refrigerants. And then eventually we'd like to get some additional certified installers up to speed on the process. Some folks are worried about refrigerant leaks because we have this kind of complex pipework of refrigerant. We're using these systems not because they're more failure prone, but because they're better. That's why so many different commercial and residential applications are going to these systems as well. We're using flexible refrigerant hose and hydraulically crimped ends, and we've had great success with avoiding leaks in the system. However, when we do work with boat builders, we just have to make sure that the junctions in the system are built to be accessible. So if if a leak ever did develop, we'd have access to it. A properly designed system lasts for many years, especially when the installation is done so precisely. Another concern that people have is that, well, it has a central compressor, so that could be vulnerable to failure. I mean, if that central compressor goes down, now we've lost air conditioning in the whole boat. That's true. And that is a risk or maybe a vulnerability. However, the system does a lot to warn us before that happens. If any of the parameters are out of sync, we're going to get an alarm in the system, not just on the main control on the boat, but if the boat's connected to the internet, we're successful. I'm sitting right at my desk where I often help troubleshoot for customers, letting them know, hey, maybe they've got a sea strainer that's clogged, or maybe it's a bigger issue that needs us to pay a visit. We can monitor all of these systems remotely. Furthermore, on some new projects, we've started to install redundant systems, especially on sailing catamarans, where instead of one big VRV compressor system, we actually put in 2 smaller units, and they have air handlers that overlap in the common areas. And then the control systems are linked. So from the user's perspective, they're actually only interacting with one air conditioning system. But should you have a failure on one side, you're only losing about 40% of the cooling in the boat rather than 100%. So for the last few years, we at BoatRx have been advocating for all of this battery, no generator design model for air conditioning. And I can tell you, and I'm sure Lexi can tell you, that from standing around at boat shows, people have kind of thought we were crazy. But we knew it was possible because this is our area of expertise, and this is why we're here. So eventually, around this time last year, we had this customer, Jack, who came to us, and he ordered a new 44-foot sailboat. He was already a Tesla driver, so we understood the concept of, charging and discharging. And he just said to us, hey, I'm ordering this boat and I don't want it to be generator based. In fact, I'm ordering it from the factory without the factory air conditioning and generator system. What can you guys do for me? I said, Jack, we've got some great ideas. We've got all this new technology. We'd love to integrate into your boat. Are you sure you want to be one of the first people in the US to have this kind of system? He was enthusiastic. He said, absolutely. And so I want to take a minute and walk you through how we think about this process of designing and installing a battery-powered air conditioning system from start to finish. So when we first take on a customer, we take an engineering retainer and get started on a proposal. And that proposal gets started with a heat load calculation for the boat. This is our air conditioning first approach to electrical design. The reality is that Jack's boat was not especially complicated. In fact, we could figure out his system on the back of a napkin, but if we have boats with maybe 8, 10, 12 or more air handlers, this calculation becomes super important. And on larger yachts, I mean, a model like this is essential. We just have to really have a firm understanding of how the heat loads differ in a glass-filled bridge deck versus the crew cabin down below. So once we understand the air conditioning capacity and how much cooling is required, we take that number and we estimate the consumption of the HVAC system under 3 different scenarios. Fully loaded in the daytime with the sun up, with the air conditioning running 24/7, with the air conditioning off, and then also the third mode with the air conditioning on minimally overnight in just the sleeping cabins. Okay, so again, we have to figure this out first because we're going to take this this power consumption, this estimate for the air conditioning, and we're going to add it to all the other electrical loads in the boat, like the refrigeration and the lighting and the pumps and everything like that. But by thinking about the air conditioning first, that's the biggest component. If we get that part right, then everything else is going to fall in line. So when we have an idea of how much power it's going to use, then we ask the customer, like, hey, how long do you want to be able to operate on batteries? And the typical answer, and we usually design for an overnight period or a 12-hour period of battery-only runtime without recharging. And that's what Jack wanted. And in reality, in his system, by the time it was done, it actually lasts much longer. So now we have the desired runtime, we have the energy consumption rate. The next thing to do is to size the battery bank. And well, we size the battery bank to be able to provide power for that duration of time. But we also have all of these other kind of conflicting demands that we're working with. We have, maybe the customer has a budget that they're trying to work within. And then there's the most important thing about putting big battery banks in boats. Anybody can guess? It's the physical size. The battery bank's got to fit. And so we need to have some measurements and have an understanding of, hey, can this system that we've just dreamt up, can it actually fit in your boat? So optimizing for these conflicting demands, it's part of what we're really good at. And you see it all over in the new electrification industries, such as EVs. I mean, all these car manufacturers are trying to extend their range without blowing the budget and by still providing fast charging. So speaking of fast charging, that's the next step in the process. So we have air conditioner capacity, total power consumption rate, battery bank sizing, and now we're like at this point where we say, well, the whole system sounds great, but it's useless unless we can put power back into it at a fast rate. So since we have to charge these batteries somehow, a generator, it honestly is still a good way to do it if there's space for one in the boat. Now, some of you might be shocked that I'm saying this after saying I hate generators, but if you pair the generator with a powerful battery charging system, we can maximize the value of that generator by using its full output anytime it's running, rather than running it all the time with varying electrical loads. So if the systems are properly balanced with a very high efficiency air conditioning system and a correctly sized battery pack, we can typically air condition the boat for 24 hours a day on just 4 hours a day of generator runtime, which is pretty great. And then if we pull back our curve here, instead of operating on the left side of the curve, now we're operating all of the time in the most efficient part of the generator, and we're increasing the value of that generator. Without a generator, we have to consider some other options. I mean, since this vessel already has a primary diesel engine for propulsion, we felt that a secondary diesel engine is unnecessary, especially since Jack's boat is under 50 feet. And until recently, it was impossible to achieve rapid charging from a regular belt-driven alternator system. Even 12-volt alternators that are commonly upgraded to 250 amp version, let's say, they produce about 2.8, maybe 3 kilowatts when they're hot and running at a high RPM. However, most stock alternators only produce about 800 to 1,000 watts. And we calculated that Jack's boat on average is going to use about 25 kilowatt hours of energy every day if he's got the air conditioning on 24 hours a day. So we need something more powerful to reduce our charging time, because if you look at these recharging times, it's just impractical. I mean, what's the point in doing battery powered air conditioning if you still have to run your engine all the time for a recharge? So we use what's called the integral system. And the integral generator is a very high output, 3-phase, externally rectified and software controlled alternator. It's rated up to 9 kilowatts of electrical power, but it actually produces more like 7 to 8 kilowatts when it's in a hot engine room. And with a large lithium battery bank, we can accept the charge in rapid fashion. If you got 2 engines in your boat, you can fit 2 integrals for double the power. And as a bonus, in many cases, this is actually free power because it's improving the efficiency of the propulsion engine while you're operating the boat. So if you're already underway, you're producing power. You don't need to start a second diesel engine. And the integral is special in that it actually increases the fuel efficiency of the motor overall, although that's beyond the scope of this talk. So if we're using 25 kilowatt hours of energy each day, and we can recharge at a rate of 8 kilowatt hours, and then we also, don't forget that while we're recharging, we're also using power. We're also, say we're using 1 kilowatt of power all the time, then we only have to run the engine for about 3.5 hours a day to keep the whole boat air conditioned for 24 hours. Now, 8 or 9 kilowatts is a lot of power generated at traditional marine battery bank voltages. If we did this at 12 volts and charged at the typical 14.4 volts for a 12-volt system, that would be 625 amps of power, of current. It's just too much. The theoretical maximum current that can be passed through a 4-aught battery cable is about 300 amps continuous, and it's even less than a hot engine room. So the only way to practically move lots of power is to do it at a higher voltage. And I think some people are still a little uncomfortable with the idea of 48 volts, but a lot of folks are coming around. It's really simple. If you want to start thinking about higher power systems and running from batteries, you need to do it at a higher voltage. And thankfully, the ABYC pushed the requirements for low voltage systems up to 60 volts. And 48, I think, is just the tip of the iceberg. That's what we're here to talk about today. But you're going to see, I think, in the future, especially when we get back into electric propulsion and even larger battery banks, we're going to see much, much higher voltages. And if we use the EV market as an example, like a Tesla operates on 450 volts power. All right, so we've got our system capacity figured out. We've got our battery bank sized. We've selected our charging sources, so we know how fast we can recharge. Now it's time to do a little engineering. And here at BoatRx, we do all of our own wiring diagrams, and we figure out the best components for the system. We lay them out, and we wire them up on screen. Okay, so we do a DC diagram for the 48 volt and 12 volt system. We do an AC diagram so we understand how we're providing power to the higher power appliances, including the air conditioning, and how we're integrating shore power in a generator if there is one. We do a network and controls diagram. We do a refrigerant pipework diagram for the VRV system. We do a condensate plumbing diagram. We do a VRV system controls diagram. And last but not least, we do an air distribution sketch. So we have a good idea of how we're actually going to deliver the cooled air to the space. And if the boat is actually getting air conditioning for the first time, it's actually quite a bit of work to fit the ductwork. And you'd be surprised that although the system parts are probably the most simple, it can actually be the most time consuming to figure out how we're going to modify the joinery in the boat and actually fit the air distribution. And I'll tell you that if you're putting air conditioning in your boat and you want to run it on generator, without a generator, you need to have proper air distribution, because if you don't, the system's just going to work too hard to try to cool a space, and it's just never going to get there. We got to deliver that cool air up high. In the case of this system, there's about 250 different types of parts. And well, this is one of the things that allows us to be really good about operationalizing marine systems installations. We have to engineer and pack a proper parts kit, which is tailored to every job. And that's because if we don't figure out everything in advance, all these afterthoughts increase our time on our job and reduce our profitability. The installation on Jack's 44-foot sailboat took about 2.5 guys, 5 weeks to complete. Now, some of you might think that's a lot. Some of you might think that's not that much, but either way, we're in the early stages of this market, and we're some of the pioneers doing this. And we want to make sure we're doing every job accurately. And I'm sure we're going to get more efficient over time. So part of this business is art, and part of it's science. The art part is navigating the demand of the boat owner and the existing technology to find the best possible fit of all solutions. The science part is checking our work and making sure the implementation follows that pattern exactly, especially when there are a few people in the marine trades that have this skill set. So you take a look here, you can just see some of the specialty tools we use in the field: a laser pulley alignment tool, a thermal camera to check our electrical connections. We use a digital torque wrench in all our refrigerant fittings. And then on the bottom right there, you can actually see this is the display for the VRV, which reads out all the temperatures and pressures. And this was displayed, the screenshot was taken while we had a nitrogen test pressure in the system, which we left in there for 5 days to make sure the system was completely vapor tight. So how did we do? We estimated that Jack's boat would use about 33 kilowatt hours per day maximum with air conditioning 24/7. And we are using Victron's remote management system to remotely monitor his power consumption. And so this is his power consumption on the boat in the month of July in Virginia. So a lot of high 90-degree days. And you can see that we nailed it. The highest consumption was 33 kilowatt hours, similar to our 32.9 kilowatt hour estimate. These numbers also make it clear that it's the air conditioning system that guides all of the thinking around the electrical system. And that's why we use this air conditioning first approach to our electrical system designs. If we get the air conditioning part right and we can reduce the power that that consumes, it just guides the rest of our thinking about the electrical system on board. This was a really complex project, and we're grateful to Jack because he was one of the first people to pull the trigger on it. And he sought out what I believe to be the best team in the country to pull it off. And we've been rehearsing for this moment for a number of years. And I have to say, I'm super proud of my teammates that this was such a great success. And we're all really excited about this future electrification of boats. We're excited because there's so much to come in the future. This year we had one Jack, and going into 2023, we already have more customers with deposits on new battery-powered air conditioning systems. And soon all of us, driven by your consumer demand, will be in an electric boating world that's probably safer, cleaner, and more efficient and cost-effective for everybody. And well, I hope. I live on my boat, so I hope to be doing it from my cool and comfortable cabin. So thanks, everybody. I really look forward. If you have any questions, throw them in the chat, and Lexi will throw them at me, and we'll make the most of this little lunch break that you've got. So thanks for joining us.
Thanks, Phil. That was awesome. That was really
My
in
pleasure.
depth and fantastic. Just starting to get a few questions rolling in now. Let's see. Some of these are very specific.
I can pull up the chat as well, just to take a look here.
Yeah. Okay, here's a good one from Eric Mitchell.
Hi, Eric.
He asked, sounds like state of the art is rapidly changing. Some self-contained manufacturers seem to only last 2 to 3 years, plus or minus 2 years. Can we expect better reliability out of these?
Eric, are you talking about the self-contained air conditioning systems? I think that's what you're talking about. Yes, 100%. The upfront cost of a VRV system is going to be higher than if you were to do it with self-contained systems. Every part of a VRV system is made of really high quality components, stainless steel, the condenser is made of titanium. They're repairable rather than kind of like the throwaway sort of concept of the self-contained system. So we know of systems, thermodynamic has been around about 10 years. We know of systems that have been out there for that long. So yeah, we represent the product because it's such a high quality product, and it is a premium, and so it belongs on premium boats.
Fantastic. Have a question from Joe about some costs. Did you put the cost of the Geno job in there, or is that
I can share
shared
that.
online?
Yeah, basically, the 44-foot sailboat with all the bells and whistles that he got installed with labor, with our travel, with every component was $130,000. That was every last penny, including our Airbnbs and gas in the vans, and that included the engineering as well. So don't forget that was the integral system, the full battery pack. We revamped both the 48 volt. He also wanted lithium for his 12 volt system. He also wanted his stock alternator upgrade in addition to the integral system and the entire VRV system. And the boat came without any ductwork. We had to do some carpentry because there was no, the supply and return registers weren't installed yet. So that job was definitely more expensive than it would cost to refit a boat that already has air conditioning.
Fantastic. Got a question from Jesse. Will VRV systems have similar efficiency on reverse cycle heat mode?
Yeah, so air conditioners are heat pumps, right? And heat pump just moves heat from one place to another by creating this temperature differential between the refrigerant in the seawater or the refrigerant and the cabin air. And the answer to your question, Jesse, is not straightforward because it really depends on the seawater temperature. So these systems, because of the really efficient condenser, and they move a lot more water through that condenser, we can extract more heat and lower seawater temperatures than I've seen from competitors' equipment. with the one major drawback that's going to be the case on every heat pump system that works with seawater, which is that we can't freeze the water in the condenser because it'll damage the system. I'll add about reverse cycle heating operation. We're working on a project right now where the customer hopes to be able to heat in below freezing temperature seawater. And that boat is fitted with generators, the battery hybrid generator system. And we're setting it up so that if that's the case, he's got to keep a generator running. We're using waste heat from the generator to preheat the seawater. And if the seawater going into the system is about 50 degrees Fahrenheit, we have the highest coefficient of performance that the system can operate in. And by doing that, we see just really high efficiencies for heating.
Very well said. Very well said. I have a question from Austin Bliss here that if can help you answer if you don't think you can answer it. But he said, is there a financial argument to go this way, or is the current argument primarily driven by the glory of quiet, no generator air conditioning?
There's definitely a financial argument. I've been actually working on an additional slide to add to this deck, to be quite honest, because I know I start off talking about like what the cost is of running a generator. And I don't have it polished up enough yet to share that because I don't want to share anything that's wrong. But I will say that if you take an air conditioning system that uses, without exaggeration, uses 50% less power than what's on the boat already, and then you pair it with a generator battery hybrid solution, so that you're no longer running the generator 24 hours a day, especially under low load conditions. Now you've switched to the point where you're running that generator maybe 4 or 5 hours a day in its peak efficiency range. And if you extrapolate that out over many years of operation and consider the reduced maintenance cost of the generator and the reduced fuel consumption and the longer life of the generator, so you're not replacing it in 3 or 4 years, there's definitely an ROI. Lexi, did you want to add to that?
No, that's exactly what I was going to say. So.
Yeah, I would be happy to, like, if a customer wanted to come to us and say, hey, here's my system now. We know that working with like going to Thermodynamica is a premium cost. I want to better understand the ROI that I might get based on, like, if you can provide me the power consumption of your existing system, how you're using your generator, how big the generator is, and all that stuff. I'd be very interested in doing that study with you to show you, like, what's the payback and how many years would it take?
That'd be great. Have a question from some of the ECYS. We have 2 questions, one from Charlotte and one from Tim about, Tim's asking about Mercuries and Charlotte's asking more specifically about Axopars. So I guess I'll just stick with Charlotte's question, is that would you recommend sticking with smaller self-contained units for smaller boats like the Axopar, or is this new VRV system aiming to be the best option for all vessels, regardless of size?
Do you want to take that, Lex? Do you want me to take a stab at it?
You can go for it.
All right. VRV is a more intensive installation process, and the equipment is more expensive. And at BoatRx, for those of you who don't know, we've operationalized the installation of our air conditioning systems for a handful of dealers, specifically those at East Coast Yacht Sales, who are the folks that are asking right now. And we're not putting VRV systems in there to date, although we're about to put one in a customer's boat coming up. And that customer decided that they wanted a premium system, and that's why we're putting it in. It will provide more cooling. It will do more cooling with a slightly better efficiency. It's going to cost a lot more. And so, Charlotte, that's because you're a boat dealer, that's a conversation we need to have, is what is the, what's the tipping point here, and what is the desire of the customer? Because at the end of the day, we just want to meet what the customer needs, and we want them to feel that they got a good value out of what they invested in for the boat.
Love it. I noticed the same thing, Phil. Here's another good question from Lynn White. Does it cost more for a new boat, clean slate like Jack's, versus doing this as a refit?
Great question, Lynn. And it depends. I'll give you 3 examples. We sometimes will, the easiest system for us to do is a new boat that comes, maybe it already has air conditioning. And so it's up to the owner if the air conditioners have value, if they want to resell them somewhere else because we're pulling them out. So all the ductwork is already done. A lot of the cabling is already run. There's already a pump. There's already through hulls. Like a lot of the components of the system are already installed, and the boat's new, so it's a clean slate. It's easy to work in. We pull all the cushions out of it. There's no personal belongings being stored in the cabinetry and stuff like that. That saves time on the job. If you take an example of a new boat like Jack's, which didn't have air conditioning, and we've discussed this with Jack in hindsight, that he actually kind of wishes that he ordered the boat with the air conditioning system, which we would have pulled out and then used a lot of the components, because the boat builder has a lot of their own custom supply and return register grills and a lot of parts that we had to source and then physically cut in, and it was time consuming, and we had to source a lot of extra materials. So that was difficult. As far as refitting a boat goes, it depends, because some refits are pretty straightforward if the boat is in relatively good shape. If the boat is if the boat's a liveaboard, let's say, and is well loved, and the cabinets are full of belongings, and the client it hasn't yet done the effort to really make space for us to come aboard, that can be a real time consumer, working around other people's things. But if the ductwork is in good shape and we already have a mounting place, and we already have, say, like a condensate drain system for the air conditioning system that came from the original manufacturer, all of those things reduce the time on the job. And so I know that's not a direct answer to your question, but it does depend.
Like some of the questions we receive and answer, the answer often is depends. Depends on the application, depends on the solution.
Yeah, it depends, but I'd like to tell you why it depends.
Absolutely. Another great question from Eric Mitchell. He says, it seems like there's a huge potential to improve user interface of programming. Let me start that again. It seems there's a huge potential to improve user interface of programming of HVAC systems. Are there affordable, smart systems that can vary operation based on predicted power available?
Great question, Eric. The VRV system has this capability, and we're working on integrating it with some of our new projects. And the way we do it is, if you have, let's say, a Victron Energy system or a Mastervolt system in your boat, or anything that can tell you the state of charge of your batteries, especially if you have lithium batteries and you're using them to run the air conditioning, if we can use a relay from that system that's widely available to send a signal, open or close switch, to the VRV system, we can program that VRV system to respond to that relay and go into a different power saving mode. We can also do this if you have a lot of solar panels on the boat, and on a sunny day, we want to run the system at full power because the batteries are topped off. And as the batteries get low, we want the system to conserve power. We can do that, and we can design for it. And as a reminder, like part of what we do, part of the value we provide at BoatRx is we do custom engineering for these projects. These are not just like swap them out sort of things. Like we look at the needs, the desires of the customer, and then we design for these different circumstances. So yes, we can do that.
Great question from Anton. Can you do it on my 410?
You got it, Anton.
The answer is yes.
Anton at Norton Yachts in Deltaville, Virginia. Thanks for coming, Anton. You know we can.
Yeah. Here's another great question from Eric Mitchell, is that marine HVAC air handlers and the compressors are very loud, but are typically drowned out by gensets or engines. Are the new units engineered quieter to account for these silenced engines?
Yeah, so with a VRV system, it's like a split system. So you're putting the main compressor, the main noise producing device, should go in a systems room or an engine room. They're quieter than traditional units, but they do still make some noise. We can also specify to Thermodynamica that they produce your compressor with some sound shielding on it to further reduce the sound. But the air handlers themselves, they can be very, very quiet. And the only noise you're going to hear is from the air. And the air itself entering the space makes more noise if it's done at a higher velocity. So if we can have properly designed air distribution, then we reduce the air velocity coming out of the vents, and we can get it down to almost silent. And Thermodynamica is a company that makes these systems and engineers them for super yachts. And they have some clients that require basically a 0 decibel limit for the air conditioning. And in small cabins and sleeping cabins, when the air distribution is designed properly, it can be 100% silent.
Here's a great question from Matt Rosa. He said, are
What's up,
electric
Matt?
boats already easier to install a new system?
Yeah, we think that if the boat is already all electric and you know, it's already been designed to have adequate charging and range for the electric propulsion, then if the boat requires air conditioning, it should certainly have the most efficient air conditioning possible. I mean, you wouldn't want to drive around a Tesla with an air conditioning system that used, 50% of its power, because it's going to reduce your range. And the same is true with an electric boat. Any other appliance that you turn on in your electric boat is going to reduce your propulsion range. But if the system's been designed for it and the appliances are highly efficient, then the whole thing can work in harmony.
Charlotte asked how far we're booking out, and booking out into February right now.
Yeah, we've got some availability still this winter.
Yeah, we do. So,
And Lexi's based in, and a lot of our team is based in New England, and I'm based in Annapolis, Maryland. And we do travel for a lot of our work, but if you're especially in those two areas, we'd love to chat with you.
so got a question from David Hoy. I might need some manipulating to get the question right, but he said, what's the approximate size of the main compressor unit that would replace, say, a traditional 8,000 or 16,000 BTU unit?
As I saying, it replaces 8 and 16. And the answer is it's called the VRV8. It's a new model. You might not see it on the website yet. It produces 35,000 BTUs of cooling maximum, and you could pair 2 or 3 air handlers with that. So David, that would be the right choice for you. That's the smallest unit, and we use it for. Remember, it modulates down. So even if 35,000 sounds like a lot, it's actually just the right size for what you're trying to do. And then Antonio, I see that there. Smallest, same answer. The VRV8.
I think Alex Rawson is trying to start a race war by getting us to comment on other installers in different countries, but we can speak for ourselves. I think that's pretty much it.
Great.
Thank you very much, Phil.
Yep.
Thank you everyone for showing up.
My pleasure.
Joining
Yeah,
our webinar today.
Let's wrap it up 5 minutes early. Everybody's got busy days to get back to, and so glad that everybody came. It's the first time we've done this sort of thing. First time I've given a webinar. So thanks for seeing me through it. And I hope that there's more to talk about here, and it's a really exciting time in boating and new technology. So until next time, thanks.
Bye guys. Bye Charlotte. See you, Jesse.
Cool. I'm signing off. See you guys.